Hello, welcome everyone. Thank you for attending today's webinar entitled Choosing Okolab Stagetop and Caged Microscope Incubator Systems, an Introduction and Selection Guide. My name is Tracy Fontaine and I am the Technical Services Manager for the Americas. In today's presentation we will introduce the Okolab catalog of products, their function, and how they will work together for your environmental needs. Before we begin, I'd like to address a couple of housekeeping items for the webinar. First, this webinar is being recorded, and after the event, everyone will receive a link via email to the recording. So don't worry if you miss anything along the way, because you can view it again at your leisure. Second, if you'd like to ask a question during the event, feel free to type your question into a chat box that will be located at the bottom right hand of your screen. These questions are actually private and they will only be seen by myself and Sylvia, today's speaker. At the end of the presentation, I'll read the questions for Sylvia and we'll have a general discussion. With all this being said, I'd like to introduce today's speaker. Our speaker today is Dr. Sylvia Fopiano, North American Sales Manager for Okolab. From 2008 until 2014, Sylvia worked as an imaging specialist with a focus on consultative sales and microscope integration, during which she specialized in live cell imaging. In 2014, Sylvia joined Okolab in the United States. And now I will turn the floor over to Sylvia.
Thank you, Tracy. Thank you everyone for joining this webinar. My name is Sylvia Fopiano and I am the North America Sales Manager for Okolab. Today, I will be talking about incubation systems for time-lapse microscopy. What are the available options and how to choose the most appropriate one for your application? For those of you not familiar with Okolab, Okolab was founded over 12 years ago in Italy, and our mission is to design and manufacture superior quality equipment for research and medical laboratories. We always prioritize quality and customer service. So last summer, we opened an office in San Francisco to offer support to our customers and dealers. Here's the agenda for today. What is time-lapse microscopy? What environmental parameters can I and should I control? What type of incubation systems are available for this purpose, and which one do I choose based on my experiment? I will then move on to describing how Okolab manufactures and designs our stagetop and cage incubation systems, and then I'll conclude with a summary. Let's begin. So what is time-lapse microscopy? Essentially, you're trying to image cells on more than one point in time. And when I say more than one point in time, I'm not referring to 30 minutes. I'm referring to several hours, possibly several days. Your goal is to acquire movies of your cellular dynamics. Maybe you want to add a pharmaceutical compound and see how this affects a specific cellular process, let's say cell proliferation. So your challenge is, how do you keep cells alive on the microscope? Now, typically, tissue culture incubators are the size of, let's say, a medium to large size refrigerator, and they have control over temperature, gas concentration, and humidity. I like to stress the importance of humidity. Let's say you're flowing a warm gas over your culture media, in this case would be CO2, for 2 or 3 hours. This may be okay. But now envision doing it for 8 hours or a day or 2. You can see how the volatile compounds of the culture media will evaporate. This will change the media composition and will affect most likely your cellular behavior or even viability. So how do you keep your cells alive on the microscope? Well, on the market, you can find two broad categories of incubation systems for time-lapse microscopy. On the left-hand side, here is what we call, Okolab calls it, cage incubation system. Now, other manufacturers call it maybe wraparound or box system, but it's easily identifiable by the presence of this transparent enclosure. You have a number of controllers for temperature and CO2, but you will always see this large enclosure. A stagetop, however, it's much more compact. It has only a small chamber and similar controllers. Let's get into more details. What is happening in a cage incubation system is that the heating encloses the entire microscope. And you are filling a microenvironmental chamber located on the stage with humidified CO2. Whereas in a stagetop incubation system, both heating and gas conditioning occur in the microenvironmental chamber on the stage. I'd like to point at similarities and differences between these two small microenvironmental chambers. In these images, we inserted perfusion tubings to remind us that our chambers, Okolab chambers, come with standard perfusion holes. They come plugged, and you can unplug them and insert perfusion tubings according to your needs. Now, what is different is that for the cage incubation system, the microenvironmental chamber has the only function of containing humidified gas, preventing it from dissipating. But it doesn't provide any heat. In fact, this little microenvironmental chamber resides, if you will, on the stage and inside an environment that is 37 degrees in the enclosure. On a stagetop system, the entire chamber has to provide heat and contain the humidified gas. For this reason, there are some wires. The lid and base are heated, and this lid is made of glass coated with a special coating. It's called ITO. It is optically transparent and electrically conductive. It will warm up and then irradiate the heat towards your sample. So how do you choose between the two, and what are more subtle differences? You can envision how a cage incubation system is extremely stable. You have an enclosure protecting your sample from, let's say, drafts or AC cycles. You never need an objective heater because your objective and nose piece both are in a 37-degree environment inside this enclosure. And let's say you're doing perfusion, or maybe at some point you want to add a compound. You could also incubate the media or compound in the same incubator so that you avoid thermal shock when you apply it to your cells. It is compatible with some IVF applications. However, because of the volume of this enclosure, it takes longer time to heat it. On average, it takes maybe 30 minutes to warm the air up inside, but an additional 2 hours are recommended to have all the microscope components at equilibrium. You can never do temperature cycles, and this is also due to the size of this enclosure. In a stagetop, it's much more easy to remove and compact. The thermal response is faster. You can envision that you're warming a smaller volume. Humidity control is active because the entire system is exposed to room temperature, so you have the necessity to warm up your your humidified gas. You can do temperature cycles. However, every time you're using an oil immersion objective, you must use an objective heater. It is suitable for multi-well plates with oil immersion objectives, but is not ideal. For those of you not familiar with an objective heater, here is represented by this yellow band, which is a heating band, which is secured in place through a ribbon. In this example, it's in green. And this is needed every time you're using a stagetop system because your objective is at room temperature, and when it comes in contact with the bottom of your well, it will act as a heat sink. It will cool down your sample. But you never need it in a cage system because in this system, the entire objective and nose piece are at 37 degrees. Let's see in more detail how a stagetop incubation system looks like. This is a general overview, and here we can look at more details. So we start with some controllers. The top box is a temperature controller. The bottom one is a gas digital controller. You can stack them together and control the stack through a single touchscreen interface. Here on the left, we have our humidity system, which is active. This means that you can select the percentage of humidity you want to deliver to your humidified gas, to your CO2. We have an optional smart box that I will talk about a little later. And here on the left-hand side, we have the stagetop chamber. Our stagetop chambers, as I mentioned, come with perfusion holes. And they never need to be filled with water because there is no moat and no water. Now, if you're not familiar with this system, you may find on the market some that once you open the lid have a moat, meaning a channel on the perimeter of the chamber. And this channel needs to be filled with water so that you maintain humidity. We don't do that. We separated our humidity system so it's not located on the stage, and we did that for safety reasons. We don't want water on the stage that can be potentially spilled. So how we measure temperature? We use a number of sensors. We have one external sensor that monitors the room temperature and 4 sensors that monitor respectively the temperature of the lid, the base, the sample, if you're operating it in sample feedback mode, essentially placing this thermocouple in a reference well, and the objective heater if you're using one, if you're using an oil immersion objective. All of this data conveys to our touchscreen interface, which is the brain, if you will. It has algorithms, and it will adjust individually, all the heatable components, but in a concerted manner. So when you're operating at a sample feedback mode, you'll have a 0.1 Celsius accuracy regardless of the room temperature variations. This is very important. Remember, we're talking about a stagetop system, so the chamber is fully exposed to room temperature. You can imagine how someone entering the room may create a draft, and this may affect, let's say, the temperature of your lid. If you're using sample feedback mode, you're ensured the maximum accuracy. In the same screenshot, you can also see the other parameters, for example, relative humidity, in this example 95%, gas concentration, and gas flow. Our digital gas controllers come in 3 main flavors. We have more than these, but these are the most common. The first one is a typical for CO2, accepts 100% CO2 and air. The second one is for hypoxia and accepts 100% CO2, air, and nitrogen. And we're using nitrogen to displace oxygen from air. And then we have one that can do both hypoxia and hyperoxia. As I mentioned, humidity is active. And I want to remind you it is important because this bottle sits at room temperature. So you want to have control over how much humidity you are delivering to your CO2. How do we do it? We use a base or a container which is heated. You place this bottle that has tubing and a semi-permeable membrane with deionized water into this container. As the gas gets humidified, rises to our humidity sensor, and then is delivered through this heated and insulated tubing to avoid condensation to your stagetop chamber. What you can select is the percentage in the range 50 to 95% with a sensor resolution of 1%. Here is how the touchscreen interface displays this information. You have your relative humidity and temperature. This example has a relative humidity of 90%. And then the temperature of our humidity sensor lid, 45 degrees, and the temperature of our base, 38 degrees. The next component of the stagetop system is the chamber. And I'm using a stage top chamber for K-frame as an example, but I want you to remember that we manufacture chambers for all stage brands and models, including upright. Now, a typical K-frame has a size of 160 by 110. This is for an inverted microscope. As I mentioned, there are built-in perfusion holes. This model has a sliding lid. And as I mentioned earlier, there is no moat and no water on your chamber. This is a partial list of inserts. There are many more than this, but I wanted you to focus briefly on the ones in the red box. So again, this is an open system. All stage top systems from all manufacturers are open. The entire chamber is exposed to room temperature, and the bottom is also exposed to the room temperature. So to improve thermal uniformity when imaging multi-well plates, you have to insert one of these perforated metal plates. But you can imagine how when you are imaging with short working distance objectives, such as oil immersion objectives, you want to use this open frame so that you can move from well to well in an unrestricted manner. Obviously, you have a little bit less thermal uniformity because of the absence of this plate, and this is intrinsic of all stage top systems. Here is an example how you would place your insert, then your plate, and then a lock. Heating and cooling is also possible on stage top systems, which is not possible on a cage system. We have several cooling systems. This is the one I want to present to you today briefly. It goes below 0 Celsius, -5 below, and up to 60 Celsius. It's very useful for researchers that study organisms that live in an environment that is cooler than room temperature, such as marine biologists that study, let's say, zebrafish or other organisms. The data logging and remote operation can be accomplished using the smart box. It's this little red device. You can use it without connecting it to the internet, and allows you to download all of the data you saw on the OkoTouch, on the touchscreen interface, meaning set point temperature, gas concentration, gas flow rate, etc. Or you can connect it, and you can see here on the back the connection to the internet, and use a web-based system that allows you to view the current status remotely or change set point parameters. And this is an example of how one of the screens looks like from your web application. You can connect through your iPad or iPhone. If you press Control, this image will appear, and by pressing on the individual tabs, you can then adjust your temperature. There's more features than that, but this is what I just wanted you to remember. That concludes our stage top incubation part, and I would like to move on to cage incubators. This is what the whole system looks like. I want to remind you that the little red box up on top here is our smart box, so it's compatible with both our systems. And I'll start by talking about the enclosure. Our enclosures are made of polycarbonate, not plexiglass, because plexiglass tends to crack. We make use of removable panels, so we have clips to install and uninstall the panels. They provide easy access to the microscope. You can remove the front panel and fully access your microscope. We also made it with a built-in LED light that you can turn on and off with a foot pedal, and then adjust its intensity with a dimmer. We thought that was important because oftentimes you're in a microscope room, the lights are off, and when you're trying to prepare your sample and place it on the stage, you can't really see. So it's convenient to have a small light available to you. We have blackout panels that can be added at a later time. Here is an example of our cage system on a Leica DMI-8 with an SP8 confocal. And in the red circle is our dimmer. This is another example on a Nikon TIE. It has blackout panels. The light, the LED light inside is on, and here you can see your little dimmer in the red circle. In this case, humidity is a little bit easier to deliver because it resides inside the enclosure. So it is at 37 degrees. It is vibration-free, and it comes with a water trap to make sure that you don't have any droplets of water reaching your sample. You can refill this reservoir from the outside of the enclosure without disturbing your experiment. So you don't have to open the door and you don't have to have warm air escaping. The controllers are digital, and the temperature controller is in this box here. It looks similar to the previous one, but now there are added components. This is actually a heater, and behind it is an optional HEPA filter. The controllers are again controlled by a touchscreen interface, which we call OkoTouch. Now, when it comes to temperature, on the market there's a variety of ways to control temperature. Some of them use an on-off switch and a manual knob to control the amount of warm air that enters your enclosure. You can envision how these are extremely unstable, and essentially they're large hair dryers. How we do it is differently. We use an intelligent algorithm to avoid overshooting the target temperature. Essentially, we gradually change the slope of the heating rate as we approach the target temperature. And how do we do it? We make use of a number of sensors. Here we have sensors located in the heater, which is this here, and then a sensor located in the enclosure itself or cage, typically is placed by the illumination pillar or on the stage somewhere close to your sample. And then we have an additional sensor that you can place in a reference well. Additionally to that, we also control and monitor our flow rate. In this example, we have a volume of air of 50 cubic meters per hour. Here you have the power of your heater and the fan speed. So all of this data converges to the touchscreen interface, which I like to call as the brain of the system. And the brain of the system adjusts all of the different parameters as you're approaching your target temperature. This ensures smooth operation. But let's say you're starting from a room temperature that is particularly cold, maybe 18 degrees or 15 degrees. In this case, you can use our fast heating feature that will allow you to reach your 37 degrees within a reasonable amount of time. Typically in the industry, these kind of systems come with a cage feedback mode. What is it? It's essentially a thermocouple, as I described earlier, that you place close to the illumination pillar or maybe on the stage. The way we do it, it provides a stability within 0.3 Celsius from the set point. However, we added a sample feedback. This it means that the system comes with an additional probe. It's represented by this thin green thermocouple that you place into a reference well. This is a standard capability in our system and allows you to reach a 0.1 Celsius accuracy from your set point. Now we can talk briefly about digital controllers. Again, they're stackable, they're compatible with our smart box, operated by our touchscreen interface, and on the screenshot you can see the concentration of your gas and the gas flow. Now, besides digital controllers, which is very similar to the previous ones, we also have manual controllers. Let's say you want to use a pre-mixed 5% CO2 or a typical 100% CO2 plus air, or hypoxia or hyperoxia. These are floating ball flow meters that are compatible with our cage stop system. Now let's talk about the chamber. Again, I want to remind you that we have chambers available for all stage brands and models, including upright. Again, I'm using the K-frame chamber as an example. It has built-in perfusion holes, a sliding lid, magnetic inserts, but we also offer optional lids, such as color illumination lid or injection lid, and so on and so forth. We can cover this in a later webinar to go in further details. Now, let's talk a minute about the inserts. This is a partial list, but I want to remind you that this time you never have to use a perforated insert for multi-well plates. You only use an open frame. And why is that? Because our chamber lives, so to speak, inside our enclosure. So it's surrounded by 37 degrees Celsius, which means the bottom, the top, the sides are all exposed to 37 degrees, which also means your objective is at 37 degrees, so you never need an objective heater. So in summary, when you have to choose your incubation system, you have to look at your own application. Ask yourself, am I using 100% of the time objective that are oil immersion, or maybe 90% of the time? Am I using those with multi-well plates? In this case, I would recommend using a cage system because you will never have an objective heater, and your objective, your oil immersion objective, can move unrestricted under your multi-well plate. But let's say you need to do temperature cycles, or maybe you want to have a faster thermal response. In this case, you could use a stagetop incubator system. Essentially, I highly recommend you consult with your Werner Instruments representative so that you can most appropriately be directed. I want to thank you for your time, and I'll be online to take any questions.
Thank you, Sylvia. That was a great presentation. I already have questions coming in, so folks are typing very, very quickly. Can you speak a little bit more about upright systems and how you manage the temperature?
So the upright system uses a similar, for upright systems, again, it depends on if you want to do a cage or a stage top. So if you're doing a cage system, it's extremely simple because the microscope, again, is enclosed and it's at 37 degrees. And your challenge, if you will, is to make sure that you can have your humidified gas contained because at this point, your objective is coming from the top. So our microenvironmental chamber for upright have an opening that wraps around your objective and allow the objective to around the stage to move and the objective to follow our microenvironmental chamber. So in a stage top system, it's similar, but this time you have heat that is provided to the chamber and not only containment of humidified gas.
Great. So I'm going to, so if you were to choose a stage top system, how quick can you thermocycle? Have you encountered that before?
Yes, so it depends on what range of temperatures you're trying to achieve. Meaning, if you are working at 23 degrees and above, your cooling is not active, it's by dissipation. So it's easier to warm up, but it takes longer time to cool down. If you're using one of our either the basic of the or the cryo system that actually have a coolant in it, it's much faster cooling down rather than because you're not using dissipation, you're doing active cooling. In terms of the time, it really depends on what is the gap of temperature that you're trying to cover, and obviously there's some limitations. But if you have if one of the users have a more specific question, we can put together a written answer for that specific jump between two specific temperatures.
Sure. How is the top of the stage top version closed to make sure that the heat and gases do not escape? Can you revisit that a little bit?
Yes. So the lid has a circular opening and it's hinged in the middle. So imagine kind of like a wrench. You open a wrench, you put it around your objective and then you close it. It's not a hermetic seal, but it's not necessary because there is positive pressure inside the chamber. So since you're pumping in humidified CO2, a little bit will have to escape. The most important thing is not to have the ambient gas getting in. If you were to seal it, you may reach a point where you're creating an internal pressure that is too high, and it could break the chamber because of the internal pressure being too high. So generally, I get this question a lot. People are concerned, but the gas is escaping. As long as there's positive pressure, your objective is to lose as little gas as possible, but mostly prevent the ambient atmosphere from getting inside.
So what are the general flow rates that you would recommend in both the stage top and cage top systems?
So it depends on what gas controller you're using. But if you're, let's say you're using the typical gas controller that accepts 100% CO2 and background air, and you want to operate at 5% CO2, the flow rate that you can select is in the range 0.2 to 0.4 liters per minute. And we recommend, an average of 0.3. You could go all the way up to 0.4, but it really doesn't make too much of a difference.
And what's the precision difference between the digital and manual flow meters?
So the digital flow meters have a 0.1% precision, and the manual have a 1% precision.
And can you use the manual CO2 controllers with the stage top system?
So you can. It's not a very common application. Usually we recommend, for cost reasons, we recommend using only digital controllers because the difference in cost is not that significant, because you would have to use a different humidity controller. But you can, absolutely you can.
Great. And then, so, and this is a question that I was curious about myself, is what is the maximum length of time that you can keep cells viable in either the stage top or cage system?
So this depends mainly on the sample for a number of reasons. Let's say you are seeding very few cells. It will take them a very long time to become confluent, but you will still have to replenish the media periodically. So we've had a French researcher doing an experiment that was 10 days long. We had another researcher sending us a video that was taken from a Friday to a Tuesday. So it really depends on the sample mostly. From the equipment point of view, the only thing that you may want to pay attention to is humidity. You want to make sure that you still have liquid water in your humidity system. So if you're using a stage top system, at 95%, you can use it for about 3 days without having to replenish it. If you're using an enclosure, again, it depends. It could be 3 or 4 days. But you can replenish it without disturbing your experiment. So that's really not a limiting factor. The factors that limit the duration are really related to your sample.
Can you go into a little bit of what's the process for fitting a microscope?
So when one decides to purchase a cage microscope, a cage incubator system, we sent a questionnaire that, because we need to know not only the microscope brand and model, but also what peripherals are connected to it and in which location. Do you have a confocal on the left-hand port or on the right-hand side, so on and so forth. We already have drawings of most of the peripherals, so a lot of the configurations, the most common configurations, are already prepared. But yeah, there may be, each and every one has some level of customization, which doesn't affect the price because they are falling within a normal range of customization. We also do really outlandish customization. We've had situations in which a researcher wanted to enclose 2 microscopes in the same enclosure with robotic arms and all sort of motorized filter wheels and cameras, and we were able to do it. And that, of course, has a different cost depending on design and materials.
And then how do the full cage Okolab systems compare to other systems that are available with temperature, oxygen, humidity, stability, along those lines?
So it depends on, there is a variety of manufacturers out there. I think some of the differences are, first of all, the enclosure is not made of plexiglass. It's made of polycarbonate. We know that plexiglass tends to crack over time. um, we have our touchscreen interface, which is extremely convenient because the digital controllers don't have any switches to turn them on and off. So you can place them on a shelf. The only item you have to have on your table is the touchscreen interface. Now, I don't know exactly how each and every other manufacturer does this, but as far as I understand it, oftentimes you have to reach into the controllers. And so if you don't have room on the table, it may be somewhat inconvenient. In terms of temperature control, others have a similar, if you want, it's called PID, this change of the slope of the heating rate, but some have on-off systems that overshoot the target temperature. What we offer standard, that to the best of my knowledge is not offered by others, is the feedback probe that comes standard with our system and allows you to have this 0.1 Celsius accuracy at the sample level. And this is important for the most challenging application where maybe you're using primary neuron cells that are extremely sensitive. You can envision how if you were to open the door of the cage, some warm air would escape. So if you're using just cage feedback mode, your heater may be activated. But if you're using a sample feedback probe, then because of the thermal inertia of liquid is much slower than the thermal inertia of air, your sample is still at the correct temperature, so your heater is not activated. So adding these capability allows the researchers to really monitor what's the cellular behavior due to the treatment and not the environment.
Thank you, Sylvia. For upright microscopes and a stagetop incubator, what is the working distance from the top to the sample?
This is a very good question, and I don't have an accurate answer right now. It also depends on which objective you're using, but I'll be happy to put together some detailed information in the document that we will send out after this webinar with the answers to all the individual questions. I wouldn't want to give an inaccurate answer.
That's no problem. So can you buy individual items as standalone items, or can you put together partial systems? What's sort of,
Yes.
let's ask the question, is what's the most stripped down version, and then, can you just buy like an objective warmer if that's what you need and work your way in?
Absolutely. So exactly. So we have available objective heaters that can be connected to a system, or they can be purchased with their own heating controller. I've had situations in which someone had already maybe an enclosure from a long time ago. It was working fine, but their gas and humidification system was no longer functional, so they decided to purchase only that component, and combined ended up with a hybrid, brand system. So everything can be purchased individually. The only limitation is that if you get a digital controller either for gas or for temperature, you have to have one touchscreen interface, one OkoTouch.
Gotcha. All right. We're going to start wrapping everything up. So any questions you guys want to ask, continue to ask them. You can also use the chat function once the webinar closes. So I'm going to thank you again, Sylvia, for a great presentation. And if anyone have extra questions, please feel free to contact your Warner Instruments representative or your Harvard Apparatus representative, and we can certainly help you out getting an answer to anything that you would like to know. We are going to send out a transcript of all the questions with all the answers, along with the link to the recorded webinar. Again, thanks everyone for attending. We're going to leave the chat open for a few minutes. Once everybody leaves, then we will close it. So over the next 5 or 10 minutes. And we hope to see you at our next webinar. Thanks very much, everybody.